specific model of this rather surprising type theory. So first, what is homotopy type theory? For those of you who've never seen it before, I'm going to kind of start from scratch and do what I can to explain it to you. So as Andy mentioned, it's based on a discovery of a connection between logic and topology. So we're starting in very, very general terms here. On the logical side, it's Martin-Löf type theory. That's a system of constructive logic. And on the topology side, well, what is topology? Well, in this case, we're interested in homotopy theory. So homotopy theory, broadly speaking, is the mathematics of space up to a kind of continuous deformation of the spaces, like the old example that you've seen on popular TV descriptions where you deform a coffee cup into a donut, that kind of thing. That's homotopy theory. So we're connecting somehow that kind of deformation of spaces with constructive foundations of mathematics. That's the kind of mind-blowing, fascinating connection that we're trying to exploit here. And what it does is it permits these computerized proof systems based on the constructive foundations to be used to reason about higher mathematics, like homotopy theory. So that's the kind of fascinating application of this connection that a lot of people are excited about, is that now you can use these formal proof systems like Coq and Lean to formalize and check, formally verify proofs in homotopy theory, like calculations of the homotopy groups of spheres on the computer. That's a kind of surprising result that was previously out of reach to computer formalization systems. So that's why there's some excitement about this new project. It also suggests, kind of going the other way, some new logical principles inside the constructive foundational system. So principles that hold in the interpretation, that hold in the world of homotopy types, can be reflected back into the logical system. What principles? Well, there's this idea of the univalence axiom, which I'm not going to say very much about at all. And then there are these so-called higher inductive types. It's a way of importing back into the system some basic spaces, like the spheres, and some basic logical constructions, like quotients, making quotients, for example, by equivalence relations, which was previously a difficult construction in type theory. And so the interpretation gives us some new ideas about how to do this. Now, there's one problem with importing new ideas into type theory. Type theory has a very good computational behavior. That's what makes it useful for computer proof assistants. So, but when you start fiddling with it, like adding new axioms and adding new constructions, then it potentially disrupts that computational behavior. So maybe you've taken this thing that was good for a certain reason, and now you've monkeyed around with it and maybe destroyed its good properties. And so we need to investigate the computational behavior of the type theory extended by these new principles inspired by the homotopy interpretation. So that's the kind of basic motivation driving this work. I'm not going to say, as I said, much about univalence, but there's a similar story that I could give you about the cubical side that would come up later and univalence. But here I'm talking about the higher inductive part and the impredicativity. So that's the connection there between impredicativity and HoTT, and in particular the higher inductive types. So I know that's a little bit much to swallow if you've never heard any of it before, but if you've heard some of it before, maybe that will kind of click for you. Okay, so let's go back to HoTT now. What is type theory? What is dependent type theory, Martin-Löf type theory? Okay, we have, first of all, dependent type theory. It starts out with some basic types. Everybody here knows product type, function type, right? You build the type theory like the simple theory of types out of some basic types, and then some basic term constructors like variables, constants, pairing, lambda abstraction. The term constructors build terms associated to the types given by the type constructors. Every type constructor has an associated term constructor, like a pair is a term of the product type, and a lambda abstract is a term of the function type, and so on. Okay, that's all kind of straightforward, familiar. What you might not have seen before is dependent types. What is a dependent type? You think of a dependent type as a family of types with indexed by a parameter coming from another type. So in this case here, I've written it like this, where we have a parameter varying over the type A, and then we have a family of types indexed in that parameter, parameterized by this variable. So that's the idea of a dependent type or a family of types. And then once you have such dependent families, you can give some type forming, there we go, some type forming operations on those. Take the sum of the family or the product of the family. And then there are associated term forming operations. So that's the idea of dependent types. We extend the system of simple types to include such dependent types. And then there are equations between terms, just like in the simply typed lambda calculus, you'll have maybe a beta reduction or an eta expansion. And then you set it up as a formal calculus of typed terms. You can do it as an equational calculus. Usually it's presented as a deductive system by rules of inference, right? If this term has this type and this term has this type, then, horizontal line, this constructed term has this constructed type, and so on. And you derive these terms of various types by successive applications of the rules of inference. It gives you a kind of deductive system for the dependently typed lambda calculus. So that's the basic setup. It was invented as a foundation for constructive mathematics, and indeed it works very well as such, but it also works very well as a basis for sophisticated programming languages and now for computerized proof assistants like Coq and Agda and Lean, and that's kind of why I'm here in the big proofs program, is because there is this tight connection between dependent type theories and Martin-Löf type theory and such computerized proof assistants. Now, this system has a kind of strange dual interpretation that most people take for granted nowadays working in the field. Some of you may not have seen it, so I'm just going to mention it briefly. I think Martine is going to talk about it a little bit more soon, so let's have a look. On the one hand, we think of it maybe mathematically, that is, the types are some kind of sets or constructive sets, and the elements are the terms that we're constructing in these proofs. We construct the elements of the sets step by step along with the constructions of the sets. On the other hand, the types are logical propositions, and we construct proofs of the propositions. So that's the dual interpretation. It's called the Curry-Howard correspondence. So very straightforwardly, a product type has as elements pairs of terms, and a conjunction has as a proof a pair of proofs. So that's the kind of correspondence there. And it gives the entire system a kind of constructive character, which I won't go into, but it's particularly interesting in, for example, the case of the existential quantifier, where anytime you can prove an existence statement, you can also find a thing that satisfies the property. So you're not going to have a situation like the one Vladimir mentioned in the discussion section yesterday, where you can give an existence proof but not know of a thing that has the property being stated. So this system has a kind of constructive character. Now, if you look back at that table, it looks like first-order logic here, right? Propositional logic, quantificational logic. It seems very natural to add one more thing over here. That would be the identity relation, which is a dependent relation. And that's exactly what we're going to do. We're going to add the identity relation to this system. So logically, this is the proposition x equals y. It's down here on the logical side. And so we add a new type here. And then we formalize it or axiomatize it by using the usual laws of identity. And the kind of interesting thing here is the terms that get identified under this new type are not necessarily identified syntactically. This gives the system a curious intentionality, and that's why the system is called intentional Martin-Löf type theory, and it maintains some good computational properties. That's the reason for doing that, which the extensional system doesn't have. However, it leads to a difficulty in interpreting these identity types under that Curry-Howard correspondence. What should the terms of the identity types be? If it was just the equality relation, there's kind of no structure there that they could have. However, since we don't have that kind of extensionality, this leads to a kind of interesting structure on these identity types. We have to try to interpret that. So let's think about what that is. So We'll go through this a little bit more slowly. Suppose we have two elements of A, and then we build the identity type over those elements, and now that identity type, as a type, might in turn also have elements. Now, if they're just proofs, then these are two proofs that A equals B. But we can still, nonetheless, build an identity type for those things, P and Q, and we can ask, what are the elements of that? These are what? Two proofs that these two proofs of A equals B are equal, and so on. And we get this tower of potentially higher, if you like, higher and higher proofs of identity, of proofs of identity, of proofs of identity, and so on. So what is this thing? Well, until whatever, 10 years ago or whenever we started thinking about this, this was simply regarded as junk in the system. And that people didn't know how to deal with this or what it was supposed to mean, and it was just a pain to have all of these identity proofs of identity proofs and so on. And that was kind of where things stood. But it turns out that this is actually meaningful information, and indeed it's a structure that one can work with profitably, and so that's what the new homotopy interpretation is all about. So here's the way the interpretation works. We already know how to interpret types as topological spaces, terms as continuous maps. This is a very old idea, and points as, enclosed terms as points of the space, terms with variables in them as maps. And now here's the new idea. If this is a space, then a term of that type, or an element of that type, we think of as a path from A to B, a continuous map from the unit interval that takes the endpoints of the interval to A and B. That's a path. And then the higher ones that we didn't know what to do with become homotopies between those paths. So here's a picture. It goes kind of like, oh, maybe I don't have a picture. I have a picture in a minute. Actually, Flores has some great pictures of this in the talk after next. So what we've done is we've done something that should be familiar to almost everyone here. We took the topological interpretation of the simply typed lambda calculus, which is an old idea due to maybe Dana Scott, and we extended it by just one new idea. And the new idea is an identity type is a path space. So if we have a path from A to B, we interpret that as a continuous path from A to B in the space X, over which we're taking the identity type. And once you put in that one new idea, everything else follows. That the rules of inference will force the dependent types to be fibrations in the topological sense. That is, they have to have the path lifting property by a simple deduction involving the rules for identity types. And then the identity types themselves have to be path spaces because they're spaces of interval or spaces of paths. And homotopic maps have to be identified. That is, the identity type on the space of functions will be a certain type of homotopies. So everything else in the interpretation basically follows from that one idea. Okay, so that's a thumbnail sketch of what's going on. So now let's look back at what happens on a particular space. Remember from your undergraduate topology class that every topological space bears the structure of a groupoid. Remember the fundamental group of a space. You take the points and we look at the paths between the points, right? And that's like a group structure. You can compose the paths and you can take the inverse of a path, right? And you can take the trivial path and so on. So that forms the structure of a group. And in exactly the same way, inside of type theory with its identity types, you have this structure of a groupoid. Namely, the identity types act like path spaces. And what I'm talking about here is something that you can prove internally in the type theory just from the rules for identity types. For example, you can prove that the identity type has to be symmetric, and then that corresponds to the inverse of a path going from A to B and then coming back from B to A that you learned about in your topology class. What you also learned in your topology class is that those operations are not strictly, right, a group. You have to mod out by homotopy. That is, you have to reparameterize the paths. Remember when you did that trick of composing paths by reparameterization, and then you had to prove that that makes the composition law associative. And that's exactly what goes on here inside the type theory. So you prove in the type theory that this structure that we just defined is a groupoid, right? But only up to homotopy, that is up to the next level of identity terms. So that's a really kind of remarkable fact. And so we get, here's a kind of picture, we get this higher dimensional structure where you have the points and then the paths and then the homotopies between the paths. That is like the higher dimensional identity terms. But it goes on. There are higher homotopies between the homotopies. So maybe a kind of, you imagine a pair of solid surfaces stretched out like this to make a ball with a homotopy filling them in, and so on up in dimension. You get a structure that looks like that. This is not a structure that the logicians made up. It's a structure that already has popped up in mathematics. In fact, it's popped up at least twice. Once in topology and once in higher category theory. And there's the kind of well-studied connection between these things. They're called weak infinity groupoids, and it goes back to a famous conjecture of Grothendieck's that these things can be used to classify the homotopy types of spaces. So there's this kind of well-studied connection, maybe a conjectured connection, between homotopy types of spaces and these weak infinity groupoids. And now here these things have popped up, kind of, as it were, out of nowhere inside this logical type theory. So that's the kind of cool coincidence there. We have these infinity groupoids. So the infinity groupoids, it turns out, impose or describe a natural structure inside the type theory, which stratifies the universe of all types in Martin-Löf type theory by classifying them according to the algebraic structure of their infinity groupoids. Every type has or bears the structure of an infinity groupoid, call it the fundamental infinity groupoid of the type, and now you can say, oh, I wonder what that groupoid is of this type, for example, of the natural numbers. Well, it's not very interesting on the natural numbers, but on some other types, like the universe of types, it might have a much more interesting infinity groupoid structure. And that structure stratifies the world of all types into different layers, which Voevodsky recognized this and really exploited it, and it becomes a very, very powerful tool in proving things about the intentional type theory. So the definition of the homotopy levels is a little bit technical. I hesitate to go to the next slide, but I'm going to do it. But don't worry too much if it looks a little bit too complicated. It's going to be explained in, I think, 2 other talks, so you get the idea. But the first part of it is easy. This is just a point. Oh, Vladimir did it yesterday, so maybe you already know. This says that the type is a point. This says that if you take any 2 points, then the paths between them form a point, if there are any paths between them, or if there are any points at all. And then the next one says that, so that's like a truth value. And then the next one says if you take any point, any 2 points, the paths between them form a truth value. So that's like being a set. Either they're equal or not, and if they're equal, they're essentially uniquely equal. And then the next one is like being a groupoid, because if you take any 2 points, then the paths between those 2 points form a set, and so on up. So the levels are like being a groupoid, a 2 groupoid, an n groupoid, and so on. So that stratifies the universe into this system of types, and this is what I was talking about. Turns out all that junk in the system suddenly is very useful information that you can use in reasoning about the types. And in fact, you can't reason about the types without recognizing this structure. Basically, you don't get anywhere. But once you recognize this structure, you can do a lot with it. And one of the things you can do with it is you can improve the kind of, here, wait, let me do my last thing. There we go. So it revises that Curry-Howard business, the propositions as types, to a new idea where the types are not all just propositions in this kind of coarse way, but the types themselves are structures, right? The lowest ones are the propositions, but then it goes up, sets, groupoids, and so on. So one of the things that it does is it allows us to reason much more precisely about types in the system and do a lot more. And one of the things you can do is you can go back to the work of Girard and Cocon and so on in type theory from 30 years ago and sharpen up some of the work they did on impredicative encodings of inductive types and get that work and improve some of the defects that were involved in that work because of difficulties dealing with identity types and identifications of terms and so on. Because of being unable to handle those issues 30 years ago, these impredicative encodings kind of got bogged down. But now that we have this clearer view of the universe of types, including these H levels that Vygotsky discovered, we can do a more sophisticated, whatever, theory of impredicative encodings, which is what I'm going to do with it now as an example of using that stratification of H levels. Okay? So this is kind of where I've been headed with this, is the impredicative encodings. Okay, what does it mean, impredicative encoding? That is a weird term. Impredicative, so in an impredicative system, like Girard's system F from Girard's dissertation, or Cocon's calculus of constructions, is a system in which you can quantify over all the types to form new types. So, and you can use this idea to form, in particular, some kind of inductive types, to encode some, systematically encode some of the other type forming operations. So for example, in system F, you don't have a primitive type of natural numbers. You do have function types and products, but you encode the natural numbers by this kind of surprising looking construction involving quantifying over all the types. And many other inductive types, lists and sums and all kinds of other W types, can be encoded in a similar way. So that's the kind of cool thing about the impredicativity. What good is it? Well, it allows us to construct many inductive types within a simpler system, that is, one that doesn't have primitive inductive types, which has a good computational behavior. For example, the system with just without the inductive types is known to have, for example, the strong normalization property. So it has a better computational behavior, and then you can construct these inductive types without worrying about, well, normalization. In particular, right, it gives you a justification for the particular rules you've used, and it gives you a computational reduction of the terms. So that's a good thing when you're monkeying around with type theory, throwing in new things. If instead of putting things in as axioms, as I said before, you can construct them, then that preserves the good computational property of the type theory, which was exactly the issue we were interested in with the higher inductive types, right? With the higher inductive types. So, okay, I already said that. So, in fact, the impredicative encodings are still there in the Coq proof assistant as a kind of residue of the original development of Coq. Now, so this is the point that I'm kind of alluding to. We could use this idea in HoTT as well to try to get some value out of it. As I already suggested, there are some kind of drawbacks of these impredicative encodings. That's the reason that the calculus of constructions became the calculus of inductive constructions. Namely, one just threw in all the inductive constructions, but not arbitrary ones, rather all the ones that are justified by the impredicative encodings. So the impredicative encodings teach us what are the right inductive types, what are the right rules, what are the right computation rules for inductive types, even if we're going to throw them in axiomatically. The impredicative system justifies the predicative system. So that's why it's worthwhile to do this. However, oh, sorry, I didn't say it right. There's a defect in the original impredicative encodings, as the specialists know, the type theorists know. Those encodings didn't quite have the right rules. The impredicative encodings in the original system F, and the calculus of constructions, have only a kind of weak elimination property, which I'll mention briefly when we get there. That is, if you're encoding, let me give you just a very kind of hand-wavy example. If you're encoding a coproduct or a sum type, A plus B, right? What you get in the old-fashioned system F and predicative encoding is what you might call a weak sum. It has the elimination property of a sum, but it lacks the uniqueness on the eliminating term. It doesn't have an eta rule, as the type theorist would say. Okay, so there's a kind of defect there, mismatch in the impredicative encoding. And that's where the HoTT comes in. Using HoTT, we can sharpen up that impredicative encoding in order to get the right elimination property on the normal inductive types. And then we can go on and try to do the same thing for higher inductive types. So let me kind of put this in a nutshell now. I want to do something for higher inductive types that is an old idea that worked out well for inductive types from a computational point of view in order to better understand the higher inductive types. But when you go back and look at the old idea, it didn't quite work right. So first I have to fix that. Then I'll take the fix and use that for the higher inductive types and try to get that to work well. Okay, so that's the plan of action here. So let's look now at the old encodings of inductive types, for example, in system F. How am I going to do this impredicative encoding? Well, I'm going to take a universe of types in the Martin-Liff type theory, this U thing here, and what I'm going to say is a universe, I'll say, is impredicative if it satisfies this formation rule. That is, if I have a family of types indexed over any type. Some people say they hate it if you point the pointer and wiggle it around like that. I'm not going to do that, but I hope you can kind of follow what I'm saying. If you have a family of types indexed over a type, this is B indexed over A, and all the value, A is anything, but all the values in the family are in U, that is, they're all small. Yeah? Then when you take the product of that family, the result is again small. That's what that rule is saying. This is to be compared with the usual rule, which also requires the indexing type to be in U, to be small. So that's the usual rule in Martin-Liff type theory, which says that the universe is closed under taking products of small types indexed over a small type. The second thing is the usual rule. The universe is closed under products of families of small types indexed over a small type. The impredicative rule says the universe is closed under taking products of families of small types, full stop. Yeah? Products indexed over anything. That's the impredicative rule. So that's what we're going to assume in our type theory, and we're going to go from there and see what we can do. The universe, by the way, is also closed under the other type-forming operations, but only the small ones, right? It's closed under sigmas, it's closed under identity types. That's all so we go from there. So now let's look at Girard's encoding of the natural numbers in the system F. It looks like, let's look at the example that I mentioned before, the sum type of A and B. So a Girard system F style encoding of A and B would be this. Now I am going to kind of wiggle around with the pointer a little bit because it's kind of, this is fascinating when you first look at it, because how on earth could that crazy business be the sum of A and B? Well, what it says is that in order to get a map out of this type into any other type X, what you do is you take a map from A into X, and then, currying this, you take a map from B into X, and that gives you an element of X, right? So in order to get a map from this gadget into X, you need a map from A into X and a map from B into X. Well, that's the eliminator for the sum, right? So that's what's encoded by that expression. It's a little easier to see if you curry it, but be that as it may. And in fact, if you take two propositions now, either in the sense of the second order propositional calculus, or in the sense of Russell's old-fashioned type theory. I think Russell first observed this encoding of the disjunction in propositions in type theory. this does indeed give you a construction of the disjunction of the two propositions. So that's kind of where this idea maybe first comes from. However, notice that I've done something kind of funny here. I've restricted the quantifier to range over only propositions in the sense of Voevodsky's hierarchy of H-types. That's what's going on here, right? I'm assuming that these things are propositions in the sense of our stratification of the universe, and then I'm quantifying only over the propositions. How does that work? I quantify over this. Uh-oh, but this is a sigma. I only closed the universe under pi's. Is that kosher? Well, I can do this little trick here, right? Quantification over a sigma like that is really a relative quantification over that. Everybody knows that. And so this does indeed reduce into a product like that. What if they're sets? Then I try to do the same thing. Okay, that's the impredicative encoding that you'll find in system F. It's exactly that. And now if you check it, this thing has the right elimination property, well, just because we built it in by the kind of naive idea that I just gave you, that this is exactly the elimination property. But there's no reason that it has anything more than that, right? In particular, it doesn't have the so-called eta rule for the eliminator. And what that means is, so this is a little bit of it's a couple of steps of reasoning. Because you don't have that eta rule, because you don't have the uniqueness of the eliminating term, you also don't have the induction property for this type in dependent type theory. That is, you don't have the dependent eliminator, which is a crucial feature in dependent type theory. You need to have not only what I'll call recursion, that is the simple elimination rule, you need to have also induction, which is the dependent elimination rule. Now, I've formulated this whole thing in terms of simple elim because it's easier to understand, but really, if we're encoding things in dependent type theory, you want elimination with parameters. That is, you want an induction principle, a dependent elimination rule. Now, fortunately, we have a very clean theory, even in homotopy type theory, of how to get induction from recursion by recent work due to Nicola Gambino and my student Kristina Soyakova and somebody else. And the way it works is, if you have a simple elim together with the uniqueness principle, that is the eta rule, you can derive from that the dependent elim, the induction principle. And that's exactly what we need here. We need that uniqueness of the eliminator in order to derive the dependent elim from the simple elim. But this thing doesn't have it. That's exactly what goes wrong with the usual impredicative encoding. Aha! But here's the rub, is that this pi is overset, and in set, it's not like prop. There's more structure. There's more structure in there. And that's what we learned from kind of analyzing these higher identity types. So this gadget here, this canonical map, is not an equivalence of types, as it would be if this was just a prop. Instead, there's an embedding retraction pair here. The canonical projection, you can easily work out what this gadget is here, this embedding retraction pair. And what we want to do now is, we want to have, so to speak, an impredicative encoding of A inside this gadget by identifying the image of this embedding under that embedding retraction pair. And what is that image? So let's try to figure out what that image ought to be. Well, what is a term of this type in general? Okay, it's a whole family of maps of this form. Let me fix the notation a little bit. I'll put this up in the exponent just to kind of keep track of what's going on. A term of this type is a family of maps like that, one for each x. Full stop. It's just that. Call it a transformation. It's a bunch of maps like that, kind of functionals. How can we cut that down? Well, there's kind of an obvious thing that we should be doing here. We should cut that down by naturality, right? We should take a family of maps like that. However, we should require that that family of maps also be natural with respect to all maps on the x and y. And that's a condition that we can express now in type theory using identity types. So the sharper encoding that we were looking for is this. We take the system F encoding like this, but then we say, okay, over this type we want the subtype consisting of all the transformations which satisfy this additional condition. And the condition is simply saying, for any map from x to y, this square commutes using this identity type. And now, this square, or this identity condition, because that is a set, this identity condition is a proposition in the sense of the level of types. And now the propositions are closed under pies. And so this whole condition is propositional. And so this gadget is a subtype of this one. So the whole thing is a propositional condition over a set, and so it gives us a subtype, which is a set again.
So when you said because that is a set,
Yeah.
a homotopy type set.
Always when I talk about proposition and set, I mean in the sense of that hierarchy of, yeah. Okay, so this encoding gives me a set, and now you can prove that that one is indeed equivalent to A. So if you use that more sophisticated encoding, and you know that that thing is a set, now you get something which is a set again. So that's our kind of new impredicative encoding. And now we can use that. So for example, the proposed encoding of the sum is going to be a subtype of this coarser encoding here. And so that's using that, what I call the main lemma, right? That's just A plus B star. And now you unwind that and you get the proposed system F encoding, and our gadget is a subtype of that. So that's what I mean when I say sharpen up the encoding. I mean, take the system F encoding and then use the identity types to reason about what's the subtype that we really are interested in. So that's what I mean. And now I'm going to do that in a more systematic way for some other types. For example, I'm going to do it for the system F encoding of the natural numbers. We're going to sharpen up that encoding using identity types. And we're going to use this observation, which was, I think, first made in a completely different setting by Martin Hyland. That is, if you have a kind of impredicative universe, the way we do have in this system, then every endofunctor on the universe, on the category of objects in that universe, has a limit. Every endofunctor has a limit. So we're going to use that, and in fact, we're going to build the limit using products and equalizers, where the product is going to be using a pi type, of course, and the equalizer is going to be using an identity type. So I'll do that. I have a minute here to go through it. So here's how I do it. The type of all T algebras is just this gadget. That's a T algebra, a set together with a map from T for any endofunctor T. Then the initial algebra is that equalizer that we had on the last slide. There's the equalizer, the limit, and it's a subtype of the type of all T algebras. Let's just unwind that type of T algebras. Well, we replace this T alg by that thing, right? Then the U of that is just the underlying X. Then the sum comes up into the product, but this thing doesn't depend on the parameter T, and so we end up with this very familiar looking expression, which is a system F encoding of what might have been the initial algebra, except now we're looking for a subalgebra of it. So the takeaway is the limit that we're looking for is a definable subtype using the identity types. So for the specific case of the natural numbers, we apply that calculation to this endofunctor, and we get Girard's encoding of the natural numbers as our kind of coarse encoding, and then we take a limit and we get the correct encoding. And now our sharpened encoding does indeed satisfy the required induction principle. Lots of other impredicative encodings can be done in this way. For example, the propositional truncation, if you're familiar with that from the old theory of types, where this was maybe called a squash type or a bracket type. Also the set level truncation, actually also the nth truncation for higher n's, but I won't go into that. Finally, just to give you a glimpse of what I said was our goal, our goal is to encode some higher inductive types. Well, Mike Schulman, who originally called attention to this idea of impredicative encoding, said maybe we could encode the circle, the one sphere, like this. That's a mysterious formula. I'll show you where it came from in a minute, but that's an enticing idea. However, it suffers from exactly the same problem that the impredicative encoding in system F had of the natural numbers. It's only a weak encoding. It doesn't have the right elimination properties. But now we know how to fix that. So we're going to fix that in exactly the same way in order to encode the one sphere in HoTT. So I won't be able to tell you the details, but I'll give you a glimpse of how it works. So why is that the right encoding for the circle? Well, what's the universal property of the circle? A map out of a circle into a type is a point of the type. I take any type, I take a map out of the circle. What do I get? I get a point by mapping the base point, and then I get a loop on that point. And a loop on the point is a path over in the type I'm looking at, and a path is an identity proof. So that's the universal mapping property of the circle right there. It's definable in HoTT. That's exactly the idea of a higher inductive type. You put the higher inductive type in by saying, what is its universal mapping property? And there it is. So that's easily definable. And now we know how to do it. We say, okay, then the circle, by that main lemma we had before, should be a limit, so an equalizer, a subtype of this coarse encoding, where we run over all one types. And now here we plug in that universal mapping property right there. So there it is. And then we play with the sigmas again, and we end up with this Mike Schulman style impredicative encoding, except that now we've quantified over all one types. So there's our proposed encoding, but now we still need to cut this down. And I'm not going to go through that because it's a little bit more intricate. That is, we need some higher coherence conditions because we're now going over one types rather than over sets. From when we used propositions, we didn't need any naturality. When we went to sets, we needed naturality. When we go to one types, we need some higher coherence, and so on up. But the same method works. And we can also do groupoid quotients and truncations and so on. So we can do lots of higher inductive types by this method. Okay, that was it. That was fun, wasn't it? That higher inductive encoding of the one sphere, I think, is a really cool and exciting new idea. And it's a lot of fun. But when you're having that much fun, you should start wondering, as I teach my children, if things are too much fun, you better ask if what you're doing is safe. So is this really consistent? Because we're kind of playing fast and loose now with the quantification over these higher types. And especially once we start fooling around with higher inductive types, the only value in higher inductive types is if you have the univalence axiom, because otherwise you don't know how to eliminate out of these things. You need univalence in order to tell you what is a family over a higher inductive type. So what we really want is not only an impredicative universe, but we want an impredicative univalent universe. So that's a new idea, maybe. Is it possible to have a universe that is both impredicative and univalent? That seems like a new condition. Well, if I just ask it in that kind of coarse form, some people are smiling, they know the answer to this. Yes, that's no problem. In any topos, the subobject classifier is already an impredicative univalent universe. Unfortunately, it consists only of propositions, right? The subobject classifier internally is a pose set. So what I want really is, in order to do more sophisticated impredicative encodings, I want a impredicative univalent universe that's proof relevant, that is, that's not a proposition. But could I have that? Well, it turns out that there are some really fascinating models built using realizability of the calculus of constructions and system F, which have a universe of which is complete and which is not a partial order. It's not univalent, but it's a starting point anyway, and that's done by Martin Hyland and others in this room, Andy and Pieter Johnstone. You use a kind of realizability category, sometimes called omega sets, to make complete category internal to another category which interprets Martin-Liff type theory. Now that's not univalent yet, but it is at least proof relevant. In fact, we can get it to be univalent by bumping this thing up by making the groupoid model inside that category. And then we get an impredicative, and now we're using the observation that the universe in the groupoid model, as constructed by Hoffman and Streicher, is itself univalent. In the usual groupoid model, it's not impredicative. Now we put those two ideas together, take the join of them, and we get a univalent impredicative universe inside the groupoids and the assemblies. But that thing now, although it's not just propositions, it is just sets. But we gained something, right? We kind of gained one more step by doing that. And now we recognize a pattern, right? We want to continue like that in order to get our impredicative univalent universe. So the way it's going to go is we're going to model arbitrary n-types by generalizing from groupoids to, hold on to your seat, infinity groupoids inside the assemblies where you have the impredicativity. So we're going to do infinity groupoids in the model of assemblies. What on earth is an infinity groupoid? Well, it's that thing that I showed you before with the higher and higher types of structure, except we have to describe what that higher structure is, and the classical way of doing that is by using what's called a Kahn complex. A Kahn complex is a certain kind of presheaf, structured gadget like that, satisfying some conditions. So we're going to make these presheaves in the category of assemblies. Now we're getting a little bit technical, but that's okay because people are working on this right now and they're interested in how it works. So the presheaves are going to be cubical rather than the classical approach, which is simplicial. In fact, the idea of a cubical Kahn complex is the original definition of a Kahn complex. Daniel Kahn worked in the cubical setting, so this is still kind of classical. So a cubical thing, and the reason we do it though is because it turns out that the cubical approach is more constructive than the simplicial approach. That was recognized first, I think, by Thierry Cocon, who's been developing a lot of this work and pushing it, that you can do the cubical approach constructively, where the simplicial approach has some difficulties. And so we're going to build what I'll call the realizability infinity topos by putting a Quillen model structure on the cubical presheaves in the category of assemblies. And again here, the insiders will know what that means, and I hope they will agree that that's the right definition. And then inside of there, we will find an impredicative universe, namely the modest Kahn complexes, the modest cubical presheaves, and that will be a univalent universe which is impredicative and unbounded in the level of its H level of its types, and that's exactly what we're looking for. And we're not quite, this is the part that's work in progress, that very last point. We're almost done, and if anybody wants to know more details, I have 3 more slides giving the details, which I don't intend to show you, but I put them on there because when I post the slides somewhere on the internet, then if you're curious about the actual construction, you can look at those 3 more slides. That's the secret inside information, and find out more details of how this works. So that's the end of my talk. Thank you very much.
Randy, and can I just say that people were complaining yesterday that they couldn't hear the questions, so if you have a question, please shout it!
Thank you. Interesting talk.
Thank you.
Now, as an old-time type theorist,
Yeah.
let me ask if you get constant time predecessor with this construction, let's say, of the natural numbers, impredicative natural numbers. And one more similar point, some of the impredicative data types don't have definable introductions, so they have weak eliminations but not definable introductions. Have you anything to say about that?
I don't have anything to say about the first question. That's an open question then that we could put on our list, but the introduction rules all follow from directly from the encodings.
No. So,
okay.
for example, the impredicative type of lambda terms, that there exists such a thing, it has no introduction rules. If it had, it would be a real type of lambda terms, but it isn't.
Okay. I guess the answer is I don't know.
Okay.
Well, thank you for this very nice talk. This makes me feel much safer because we had been developing the probabilistic programming based on your work on this. I'm happy that it's out. What
Work in progress.
I trust
Don't be
you
too
that,
safe.
this will work out.
Yeah.
So what properties do you need from the assemblies?
From the assemblies, I need it to be locally Cartesian closed, right? And so one thing that we try to do is we try to avoid any use of infinitary colimits because the assemblies are not complete, as you know, and even omega colimits have to be recursively indexed, and so we try to avoid that. And so what that means is some of our work can't take the classical approach using the small object argument for the insiders, or even Richard Garner's small object argument is not available because we don't assume the assemblies to be co-complete. So that's a technical issue. So basically the setting that we work in is simply a locally Cartesian closed category with a small, with a natural numbers object and then an internal universe. So.
Two more questions. One.
Yes. I'm trying to understand how some of this interacts with Girard's paradox. So your
Oh yeah, that's a good question, yeah.
your impredicative universe, it seems that if you could construct the power set of the universe, then
Yes.
you're in trouble.
Yeah, from which it follows,
From which it follows that all types are inhabited.
no? If I could, then I'd be in trouble, from which it follows,
Assuming he's not in trouble.
Well, then you can't construct the.
yeah, that's the answer to your question.
Well,
You can't construct a power set.
Well, if your pi-type construction allows you to have the universe and then the booleans on the other side, then you have the power object. That's not.
The Booleans is not a power object. You're doing the reasoning yourself in real time. You can construct, you can take the power object and the double power object with the Booleans, you can take the function space with the Booleans and the double function space with the Booleans, and you can find a fixed point of that endofunctor, and so you can find a type A, which is isomorphic to A arrows bool, but that will not be the double power set of A. So you cannot construct the power set in there, otherwise you'd be in trouble. It's an observation that you can find in an old paper of
Just
Martin
one final
Heidelberg.
question, Pieter.
Yes, it seems that you're suggesting that we work in the original calculus of constructions plus the univalence axiom. Anything else?
That's it. I need the function extensionality, but that follows from univalence, and that's it.
And can you encode all the hits in the hot book?
Not all of them, not all of them. But that's kind of experimental. How many can we do? Well, at this point, we can do all the ones that have a finite n level. So we can do all the truncations, we can do lots of quotients, we can do the one sphere. What about the two sphere? That has infinite homotopy level, surprisingly. It's not an n-type for any n. So we're stuck at the two sphere already. So we can do anything that's a finite n-type, but something that has an infinite h level, and there are some examples of things that have infinite h levels, then we don't know how to do it. That doesn't mean we can't do it, but we need some more thought. And in particular, we need a certain trick that we have kind of a coarse idea of, but it's work in progress. Good question.
Okay, we have to finish there, so let's.
Okay, thanks, Andy.